So the daily problem is remove stones to minimize the total. You can pause to read it. But the gist of it is we're given an array and a number. And in the array piles, we can divide one of these numbers by 2 every step. And the number is the number of steps that we get. So here we'd want to divide 9 by 2. And if you look at the semantics, we're taking the floor function when we remove half. So this would turn to 5. And then we're dividing 5 by 2, or more aptly put, we're taking away half of 5, rounding down. So we're taking away 2, so this would turn to 3. 3, 4, 5. Or you could say 5, 4, 3. You could take from the other 5. It wouldn't really matter. This is a perfect place to use a heap. And a heap is O of n for pretty much every, you don't retain the original order when you heapify an array, but it's O of log n for pretty much every operation except O of 1 to retrieve the minimum or maximum. You can just make everything negative, which is pretty much what we're going to do. So the first thing we want to do is make everything negative. We want to say piles equals negative x for x in piles. So right off the bat, everything's negative now. And then we want to heapify piles. So if we print this now, if we print piles, and then we'll just return whatever, 12, because that happens to be the answer, and I like to see green. It's going to be, okay, we can see that all these are negative. And heaps are kind of an arcane, confusing order. It's sort of simulating a tree with an array, so it's not really worth looking at the relative order, but one thing we can surmise is that the largest element is first. Similarly here, the largest element, 9, or the heap is thinking it's the smallest because it's negative 9, is first. And we can use that. So we can do something really simple. We can just say for I in range k, and then there's heap push is a function, so we could say heap push 2, and then it would add 2 to this heap. It would add 2 to piles. We would need to say heap push piles and 2. And then if we, let's just say return 12, print piles, we can see it added 2 2s, and they're at the end because they're not the smallest element. They're the largest element because they're the only positive one. Or, so there's heap push and there's also heap pop. And let's say print heap pop. And what this does is it takes the smallest element away. Oops. We need to say heap pop piles. This is like a built-in function, so we don't say piles dot heap pop. We say heap pop, and then piles is the thing that the function's operating on. So we can see that we pop the 9 and then we pop the 5. And then if we print piles at the end, both of those are gone. We're just left with negative 4. We can see if we just popped everything, we're going to get this sorted order to it. And you can say, oh, wait a minute, this is O of log n to do this heap pop function, whereas sorting is O of n log n. So is that a way around that? But the answer is no, because heapify is n log n. And also, if you wanted to sort by heapifying it and then popping every element, you have to heap pop n times, so it still winds up being n log n. Anyway, there's heap push and heap pop, and then there's also, surprise, surprise, heap push pop, which we don't actually want to use. It's close, but what we want to use is heap replace. And they're almost exactly the same, but the order is different. Heap push pop, I believe it pushes and then pops. Heap replace, it pops and then pushes. So we want to say heap replace heap, and what this is going to do is it's going to pop the smallest element, aka this 9, and then we get to push something as the second term here. So then we say heap at 0 over 2. And then all we have to do is say return negative sum of piles. Oops, not heap, piles. Cool, and now we can see we're returning 12, and if we print heap here, piles, not heap, if we print piles here, we can see that it did successfully. It popped the 9, it added a 5, it popped one of the 2 5s and added a 3. But again, they're all negative. This is a very common thing that happens with heaps, where you're working with everything negative. And the reason we do that is to access, that means piles at 0 will always be the largest thing in piles, but negative, as opposed to if we didn't make everything negative, then it would be popping and having the smallest thing. The only other thing to point out here is this over 2 operation is actually doing, it's very convenient that this is negative. Because if we just said like 9 equals 9 over 2, which almost is exactly what this is saying, it's saying pop the smallest thing, add the smallest thing over 2, aka integer divided by 2. So 9 integer divided by 2, we can actually just print that. 9 over 2, this should print 4 now. Yeah, but an important thing is that this always rounds down. So this is rounding towards 0 right now, but if we said negative 9 over 2, this is going to print out negative 5. Because it said, well, it's negative 4.5, but you got to round that down. Which is exactly what we want here. So the fact that we're turning everything negative for the heap actually serves a dual function here. And if we run it, it should be very fast. My first run through, I got 100%. Yeah. Feels good.